Tunisia, 1943. American forces had been pushing across North Africa for months. The desert campaigns had become a test of industrial capacity against military doctrine. German forces fought hard, but with each month, they faced more American machines. On a ridge outside Gafsa, a wounded American tanker abandoned his machine and fled into the dunes. The tank, an M4 Sherman, was remarkably undamaged. German recovery teams found it intact. They brought it back to Kummersdorf, the weapons testing center north of Berlin, where all captured Allied equipment was examined. German engineers gathered to see what the Americans had built. What they found changed the way they understood mechanized warfare forever. The Sherman's exterior was unremarkable. Welded steel construction, relatively thin armor, a turret that looked crude compared to German designs. But appearances deceived. When German technicians began disassembly, they made a discovery that troubled the senior engineers. Every rivet was identical. Every weld was consistent. The armor plate showed no variation in thickness. The steel quality was uniform across the entire hull. This was not craftsmanship. This was industrial precision replicated tens of thousands of times. German armor was hand-finished, built by skilled workers who adapted each plate individually. The Sherman had been designed for mass production. 2,000 factories could build identical sections. They would fit together perfectly without adjustment. The implications were staggering. The armor thickness disappointed some observers at first. The Sherman carried between 50 and 75 millimeters of steel, depending on the variant. German Panther tanks mounted 80 millimeters on the glacis. The Tiger carried 100. But when German engineers measured the slope of the Sherman's armor, they realized their mistake. The glacis plate was angled. The effective thickness was far greater than the actual measurement suggested. At 0 degrees slope, 75 millimeters of armor seemed thin. But at 45 degrees, that same plate was equivalent to 106 millimeters of straight-on thickness. American designers understood ballistics. They had calculated the angle to maximize protection without adding weight. The Sherman was lighter than the Panther. It carried more armor than the Panzer IV. It achieved this balance through intelligent design, not through the accumulation of steel. The suspension attracted immediate attention. Independent torsion bar system with vertical volute springs. The system was simple. The system was durable. The system could be repaired in the field with basic tools. German tanks used complex interleaved wheel systems that required half-track recovery vehicles to remove a single broken wheel. The Sherman's wheels could be swapped by a crew in minutes. Every wheel was identical and interchangeable. Every spring could be replaced without removing the entire suspension. The efficiency was undeniable. German engineers had spent years refining the Panther suspension. It was technically superior. It was also fragile. It broke frequently. It required specialized tools to repair. It immobilized tanks for days. The Sherman's simpler system kept American tanks fighting. Beneath the hull lay the power plant. The Wright R-975 radial engine, 9 cylinders arranged in a circle, producing 400 horsepower. At first, German observers found it unusual. Radial engines belonged in aircraft, not tanks. But when the engines started, they understood the reasoning. The R-975 fired with smooth precision. No misfetus, no Rafaeling, no vibration that required compensation. The engine ran continuously at high power without mechanical failure. The cylinder heads were easily accessible. Spark plugs could be changed in minutes. The carburetor was standard across thousands of vehicles. Replacement parts were everywhere. German Maybach engines in the Panther produced more power, but required hand-tuned fuel systems. They would fail after a few hundred hours of operation. The Wright ran continuously. The American approach prioritized reliability over performance. In mechanized warfare, the tank that keeps running wins. The transmission was a revelation. 5 forward speeds and 1 reverse, synchronized with a simple clutch system. It could be serviced by average mechanics. Every component was standardized. The neutral position allowed towing. The design allowed recovery. If the transmission failed, American crews could replace it in the field. German Panther transmissions were engineering marvels. They were also nightmares to maintain. Tank crews had to remove them completely for any repairs. That required evacuation. That required days of work. The Sherman's crude transmission was a masterpiece of logistics thinking. It kept tanks mobile. German test pilots took the Sherman to the Kummersdorf track. Tank warfare officer Major Hartman commanded the evaluation. His report would determine whether Germany's tank doctrine needed revision. The first test was simple. Raw speed on flat, prepared ground. The Sherman reached 40 kilometers per hour. The Panzer IV achieved 42. The Panther reached 55. The Germans seemed to have the advantage. Then Hartman ordered the cross-country tests. The tanks were driven through terrain designed to punish suspensions. Steep hills, mud pits, water crossings, rocky ground that would damage tracks. Everything that real warfare entailed. The results contradicted the simple speed measurements. The Sherman's wider tracks distributed weight more effectively. Ground pressure measurements showed 14.1 pounds per square inch for the Sherman compared to 16.5 for the Panther. In mud, the Sherman maintained better average speeds than either German tank. On soft ground, it was actually faster. The German tanks were sinking slightly into the earth. The American tanks stayed on top. In a country where half the battles were fought in mud, this mattered infinitely more than top speed on highway. The Sherman was designed for the reality of war. German tanks were designed for German roads. The gunfire tests were brutal. Sherman versus Panzer IV. Sherman versus Panther. The results were predictable and tragic. The Panther's 75mm gun could penetrate the Sherman's armor at nearly all combat ranges. The Sherman's 75mm gun could damage the Panther but not penetrate reliably. The German tank held the advantage in pure firepower. But the tests revealed another factor. The Sherman's gun stabilizer allowed accurate shooting while moving. The Panther's gun had to stop to aim accurately. In real combat, this mattered. The American tank could fire and maneuver. The German tank had to stand and fight. Speed was irrelevant if you could shoot while running. German engineers measured crew efficiency. The Sherman's interior was spacious. The radio was in the turret, not jammed in a side compartment like German designs. The gunner had a clear sight picture. The commander had a rotation periscope. The driver had a smooth steering wheel, not the complicated dual-lever system German tanks required. Everything in a Sherman was designed for efficiency. Everything in German tanks was designed for firepower or armor. Crew comfort was secondary. In a 12-hour battle, crew efficiency determined which tank stayed in action. Tired, cramped crews made mistakes. Rested, comfortable crews fought effectively. American design prioritized the human element. The ammunition storage was another revelation. German tanks stored ammunition loosely in racks. A penetrating hit would ignite stored rounds. The tank would explode. The entire crew would burn. American tankers called them Ronsons because they lit up like the lighter. Germans called them Tommy Cookers. The Sherman's designers had learned from this. Later models carried wet ammunition storage. Double-walled containers held water and ethylene glycol between the walls. A penetrating hit would ignite the water, which would spray into any fire, extinguishing it. The tank would survive. The crew would survive. American engineers had designed the tank to save lives. German engineers had designed their tanks to kill the enemy. The Sherman was designed to keep fighting. Major Hartman compiled his findings into a report classified top secret and sent to the Reich Army Command. The conclusion was grim. This tank represents the culmination of American tank design philosophy. It combines firepower adequate for most tactical situations with armor sufficient to survive anti-tank fire. Its suspension is robust. Its engine is reliable. Its production is consistent across all units. But most significantly, it represents a design philosophy fundamentally different from our own. The Americans have designed a tank for mass production and continuous operation. We have designed tanks for technical superiority and individual excellence. In a long war against an enemy with unlimited resources, their philosophy will prevail over ours. The memo circulated among senior officers. Few responded. Few wanted to admit that German engineering might be inferior. Few wanted to accept that the war could not be won through technical superiority alone. German designers proposed a new tank using the Sherman's lessons. The Panther II and Tiger II would be revolutionary. Sloped armor, improved suspension, better design hulls, But these tanks came too late. Production of the Panther II was canceled. The Tiger II was built in limited numbers. Meanwhile, American factories were producing Shermans by the thousands. By 1944, American factories built 2,000 Shermans per month. German factories built 700 Panthers and Tigers combined per month. The math was simple. American production would overwhelm German quality. A well-designed cheap tank produced in numbers would defeat an expensively designed superior tank produced in limited numbers. American industrial power had translated into tank superiority. In combat, the Sherman proved resilient. American tankers learned tactics to compensate for the firepower disadvantage. They hunted in packs. They flanked heavier German tanks. They used terrain. They used speed. When a Sherman was destroyed, another immediately replaced it. When a Tiger was destroyed, it was irreplaceable. By 1945, German tankers had lost the advantage. The Shermans controlled the battlefield not through superior firepower, but through superior numbers and superior reliability. They broke down less often. They were repaired faster. They were replaced immediately. The German tanks were better machines. The Shermans were a better system. At Kummersdorf, the final test was a simple comparison. 3 tanks drove identical courses for 12 consecutive days. The captured Sherman, a Panzer IV, and a newly delivered Panther. After 12 days, the Sherman had completed all courses without a single breakdown. The Panzer IV had required 1 engine repair. The Panther had required 2 major repairs and replacement of hydraulic fluid multiple times. The Sherman had consumed less fuel. The Sherman had covered more miles. The Sherman had never failed. German engineers updated their report. This American machine represents not a revolutionary design, but an evolutionary perfection of fundamental principles. It is less impressive than our newest designs. It is infinitely more practical than our best tanks. It represents what happens when engineers are required to build machines that do not break, that consume less fuel, that can be repaired by ordinary mechanics, that can be replaced by identical machines from different factories. It represents the industrialization of war. When Allied forces crossed the Rhine in April 1945, the final battles were fought in German territory. German tankers had lost the technical advantage years ago. The Sherman's superior reliability and infinite numbers had won the battle of attrition. At Kummersdorf, the final Sherman test specimen was destroyed by bombing in the final days. The engineers who had studied it fled westward with their notebooks. Some would later work for the Allies. Some would work for the Soviets. All would carry forward the lessons of the Sherman. That this American tank had changed the way the world thought about armored warfare. That reliability in production mattered more than perfection. That a good enough machine made in sufficient quantity would defeat a superior machine made in insufficient quantity. That industrial power had become the ultimate weapon. The Sherman was not the most advanced tank in World War II. It was not the most heavily armored. It was not the most powerfully armed. But it was the most practical. It was the most reliable. It was the most producible. In the end, these qualities mattered more than any other factor. After the war, the lesson would reshape tank design worldwide. The T-54 Soviet tank incorporated Sherman lessons. The Chieftain and Leopard tanks of the West incorporated Sherman lessons. Every modern tank still carries forward the Sherman's philosophy. Simplicity, reliability, maintainability, producibility. In Kummersdorf, German engineers had written an epitaph for German tank design. American engineers had written the future of mechanized warfare. The Sherman had ended one era and begun another, not through superiority, but through excellence in the fundamentals, not through revolution, but through disciplined execution of proven principles. When the ruins of Kummersdorf were discovered by Soviet forces, they found scattered documents. One memo survived, its title still legible beneath the soot. It read simply, "Evaluation of captured American M4 Sherman tank." The first line of the introduction had survived the fire. It read, "This machine represents the end of our tank design philosophy. American industry has won the war we did not yet comprehend we were fighting."